All right. Good afternoon, everyone. Good to see you. Thank you for being here. And let me just get some things out of the way. Awesome. And well, thank you for coming. This should be a quick session because the primary motivation I had for making this small series was back in 2019. Actually, the transition to spring of 2020 when COVID hit. Most everyone had to, forego labs and go into online teaching and all of that. And the main issue with that is that, well, you can no longer run experiments. So a lot of undergraduates and graduate students like myself had to turn into computational chemistry. The issue is if you start looking online for like resources to learn a thing or two about computational chemistry, it's either all or nothing. You're either going to find a 15-part lecture series by probably some university in Minnesota, which is a pretty complete and fairly reasonable approach to this, or you're going to be on the other end of the spectrum where you have only a 3-minute video from a professor in Columbia presenting their research group. And there doesn't seem to be much of anything in between unless you happen to remember a course you took in quantum chemistry. And so the idea with this small talk is really to just provide a bird's eye view of quantum chemistry and how we actually compute stuff about molecules on a computer, while perhaps presenting some of the nuance on how to actually do it yourself and some of the nitty gritty of the different methods, their limitations, and perhaps most importantly, just highlighting some of the general concepts behind simulating the world in a machine, which I believe is very, very straightforward. This is essentially, there are like two clear sections to this presentation. The first section is pretty much the basics of how things work. The second part is a bit more applied, and it should take about 50 minutes because otherwise I think it just drags on for too long. I'll be happy to take any questions at the end. And with that, let's jump right in. Like when I say quantum chemistry, I'm going to be primarily referring to the scale of the things we're dealing with. As chemistry, we're going to be primarily focusing on small scale stuff, and the smaller the system, the more relevant the quantum phenomena become. Getting the basics out of the way, we tend to describe things, if you recall from any lecture you may have taken, as a wave function psi, which can be used to represent anything. In the realm of chemistry, we're most interested in the motion and behavior and properties of electrons. It's worth remembering the square magnitude of psi gives you a probability, and there are these things in quantum mechanics called operators, the most important of which is arguably the Hamiltonian, which can be thought of as a function of functions. It's a function you apply to your function psi, which describes your electron, and that's going to give you one of the properties of that function. It's perhaps most intuitively thought of as a question. It's a question you're going to be asking psi, which will find you an answer, even if we cannot precisely know what psi looks like. And the best part of this, when it comes to quantum chemistry, to a more pragmatic approach in simulations, is that this description of any system follows the variational principle, which essentially states that if you have a system and you do not know exactly what it looks like, but you have a guess for it, the energy you're guessing is always going to be greater or equal to the lowest possible energy of the system. And that's like pretty much an obvious statement, right? Anything is going to be greater than the minimum. But at the same time, it's a very useful tool because it now allows you a way to filter off and find the best wave function, that is the best description of a quantum mechanical system by using this principle. Because if you have two wave functions, one of which has a lower total energy, you know you're going to probably be closer to the actual ground state of your system by the variational principle. And as a result, people start treating psi, or the wave function of the system, as this all-knowing oracle, which has all the information you can possibly want, information which you can probe through the operators, which are the questions you're going to be asking. But at the end of the day, psi is just a function, right? It doesn't carry any absolute physical meaning. People can discuss that all they want, but at the end of the day, it is just a function. And it's a function you have to build yourself if you're dealing with systems that are more complex than just a few harmonic oscillators and analytically solvable problems in quantum mechanics. And one good way to start building this psi is through the famous linear combination of atomic orbitals. Consider you have the bond between a carbon and a hydrogen atom. And you know intuitively and chemically that there's going to be some electron sharing, right? The electron density is going to be spread between the two atoms. And it's going to look something like this diagram. And there are many ways to build something looking like this. You can use just one s-type orbitals. That is, you can just take the approach on the left and add together a bunch of sphere-like regions in space, call that a function, and use that to approach your bond. Or you can do what organic chemists do and play around with the notion of hybridization. You can imagine that there is this mixing between the p and the s-type orbitals in carbon, put them together and see how well that resembles what you're trying to emulate here. And that's essentially the main approach used in computational chemistry to build this all-knowing oracle that is the wave function, right? You're going to pick an atomic orbital. In this case, we label it phi I, and we add them together to approach your total wave function psi. And of course, this is done linearly because computers love linear algebra. It's easy to deal with. You can play around with matrices, and you're going to attach different weights to these atomic orbitals, giving you this molecular orbital. Once you have that, you apply the variational principle and you start looking for the lowest energy you can get. So you start varying the coefficients, A sub I, in order to minimize the energy of your system. And it's worth noting here that, as we will see a bit later on, these functions are purely mathematical. We adopt them to be atomic orbitals because we have the analytical solution for those, right? The hydrogen atom is a solvable problem in quantum mechanics. However, anything much more complex than that kind of like runs away, and it gets pretty intractable very quickly. But what exactly is the molecular energy of an atomic orbital, or the energy of a molecular orbital? Well, like anything in physics, it can be broken down into a kinetic and a potential part. The kinetic part is described by this first term here. The second part is a bit more straightforward. It's basically the product between charges divided by distance. It's a standard Coulombic-like electrostatic potential. And the second and nightmarish part of your potential energy is described by the interaction between the electrons in a given molecular orbital and all the other electrons in the system, right? Which leads us to my first digression, and perhaps the most important one, the fact that in quantum mechanics, at least chemically, you're going to probably be dealing with something way worse than the three-body problem, right? You may recall from Newtonian mechanics that you can solve the gravitational laws of motion for two bodies pretty easily. That gives you a bunch of like conical intersections type curves. There are perfect solutions to your system. But as soon as you add a third body in there, just sun, earth, and moon, it's already nightmarish to solve. I don't think it can be solved analytically. You have to use a numerical approach. In a sense, a molecule is that, right? The issue is we have way more than just three bodies, right? If you pretend the nucleus of a boron atom is the center of your solar system and you have a bunch of planets around, you have a lot, way more than three bodies, depending on how many electrons you're going to have in a molecule. And even worse, you do not know their shape, right? We know from like planetary behavior that you can treat planets as point-like when it comes to gravitational attraction, but you can't do that for electrons because their shape ends up being spread over space because there is that inherent uncertainty to quantum mechanical phenomena. And that's the type of unusual and funky and nightmarish attraction you're trying to describe with this last potential term, which essentially involves this double integral across two different electrons, one for each spin in your molecular orbital, and the weight of which is defined by the product of those coefficients we defined previously when building up the wave function, right? Which makes sense. The repulsion between electrons is going to be proportional to the location they occupy in space, which is captured by the shape of the total molecular orbital I'm building up from those smaller functions. And that leads us to the first main problem, right? What I am seeking here are the coefficients A sub I. those are the coefficients that are going to tell me what the function looks like. And then from that, I can ask more meaningful questions. But if I'm trying to build this and I need to know the coefficients in order to find the electronic repulsion, in order to find the energy, we now have this circular reasoning, right? We have this closed loop where you need both pieces to solve the same puzzle. And so how do you go about doing this? And this is how you land on the famous Hartree-Fock method, right? And it goes something along what I described previously. So just summarizing it up, you're going to pick a basis, which is going to be the set of functions you're going to add together to describe your system, right? Conventionally, we use atomic type solutions. We take functions whose solutions we know analytically, whose form is explicit and easy to deal with. And from that, you're going to guess a geometry. You're going to estimate what you want or you expect your molecule to look like. And from that, you're going to start computing the energy of your system. That involves computing the overlap, 1 electron and the 2 electron integrals. And then in order to actually properly compute the 2 electron integrals, you're going to have to first guess the values of those coefficients. You're going to say, you know what, this orbital should look something like this. And once you have that initial guess, you can then find an initial energy. And from that, you can start solving the Hartree-Fock secular equations, which are essentially a reformulation of the variational principle. I do not show it explicitly here. It gets into the more mathematical description of quantum mechanics. But at the end of the day, it's just a way of saying, look, if what I'm looking is the lowest possible energy, the system whose description has the lowest possible energy of the system, I'm going to have to solve the secular equations. It's this circular reasoning between finding the ground state and finding the system with lowest energy. They are equivalent statements most of the time. And once you have that, well, you can then find new coefficients A sub I. And then you ask the simple question, are these new coefficients similar to the ones I had previously? If they are not, you're going to take the new guess, you're going to plug it in, and you're going to plug and chug for as long as you need to. But if eventually you define that, yes, they are similar enough, well, then you're essentially done, right? You found the lowest energy description of your system, which by the variational principle, we know is probably very, very similar to the actual solution of the system. So it's a numerical solution. It's a great approximation. It can get you pretty far. However, bear in mind that in step 2, we actually guessed the original geometry, right? So you now have to consider tweaking here and there each of the possible degrees of freedom of your system. So maybe you want to stretch it on a little bit, contract it a little bit, and you can use different approaches to see how things go and which is the best way to do this. But at the end of the day, it's a lot of computation. It's a lot of integrals, and it's just, at the end of the day, nightmarish. That said, at the end of the day, the wave function is most useful for that, right? Geometry optimization. Thinking broadly, chemistry is all about geometry optimization. You are going from reactants to products, you go through some intermediate steps, but if you take a look from afar, a chemical reaction is just a rearrangement of atoms. You're going from one geometry to another geometry, and finding the local minima, the states that minimize the energy, is essentially perhaps the most valuable piece of information you can harvest from a system. That said, it's much easier said than done, because as you would expect, as your molecule gets bigger and bigger, you're going to start dealing with so many degrees of freedom that ensuring you have the proper global minimum is very unlikely, right? You have way too many variables, and you cannot be sure that you haven't hit a local minima out of which you can't escape. And for that, you have plenty of methods to find a nice way to escape these local minima. And here it's worth first presenting the notion of integration over phase space, which is a fancy name for essentially computing the average / expectation value of something. Mathematically, it takes on this form, the expectation value of a function pi, that let's say pi is the polarization of a system, which is dependent on the coordinates r. You're going to integrate, so essentially calculate this weighted probability of the value for your function pi over the different spaces, and that's going to give you the expectation value of pi. The most intuitive way to consider this type of mathematical operation is to consider the pendulum, right? The expectation value of position for a pendulum is, well, we know the pendulum goes from left to right, from right to left, back and forth. So it should be about the middle, and that's what you get as you would expect. And you can do this for essentially all properties of a molecular system. In fact, you're most interested most of the time in the expectation values of geometries, because you have usually a molecular ensemble when you're playing around with chemistry. And so each individual molecule will not hold the proper optimal geometry all the time, but the average molecule is going to look something like that. Issue is, of course, phase space is huge. It's going to be a 6n dimension type thing because of the 3 degrees of translational motion plus the 3 degrees of rotation in your system. And you need to find a way of filtering away the local minima without killing the global minima. And one way to do this is the famous Monte Carlo method, which goes something like this. And bear in mind, this is a very crude approximation, but it's also a very neat concept worth introducing. Essentially, if I have a molecule, let's consider a change in geometry, and I go from geometry R1 to R2. I compute all those integrals we talked about, and I compare the energies. If the energy for the new geometry is smaller than the previous one, by the variational principle that's closer to our final geometry, let's accept that motion, let's make that change. But if not, if that change actually raises the energy, you're going to compute the Boltzmann ratio for that change in energy, and you're going to compare that to a random number, right? For those familiar with statistical mechanics, this is a pretty standard approach, right? If not, you can think of it as a way to compute the likelihood of transitions involving changes in energy of a system. And if that number happens to be bigger than the random number you selected between 0 and none, you accept the move. And with that, suddenly energy barriers become congruent. And that's very nice. If your energy is not, you reject that motion and you try a different geometric arrangement. And with that, you can start getting some very nice mathematical expressions for the expectation value. But most important, you have a way to escape local minima. So for example, in this case, as we go from R1 to R2, that's a clear drop in energy. Going from R2 to R3, a clear drop in energy. By going from R3 to R4, that's a raise in energy, which wouldn't be normally allowed if you are not using any type of approach. However, with Monte Carlo, there is a chance that eventually your system can overcome the barrier, and then it can drop down from R4 to R5 all the way to R6, which is clearly lower in energy than your previous local minima. Another way of doing this type of escaping the needle in the haystack problem is to appeal to annealing, which also introduces the second, perhaps more general concept we're going to be talking about. And it involves essentially thinking of things in a continuous manner. Annealing goes with essentially changing the temperature of your system gradually. You start with the system in a high temperature, that is, you allow various sorts of energies, and as time goes on, you randomly compute geometries for your system. And the more geometries you compute as time goes by, you start prohibiting the presence of high energy elements in your system. That would be equivalent to the sort of like greenish line here. It's as you lower the temperature as time goes by, you're going to start forcing your system to, on average, that is the expectation value for the geometry, to gravitate towards the global minima. That way you avoid this region, because if you're a random geometry, as temperature goes down, you're going to be less likely to be here. You're going to be more likely to be in this open region of your space. However, one great question worth asking here is this the best approach, right? Is the wave function the best way to do it? And the truth of the matter is, for chemists, it is not. If you're a pure physicist, it may be. However, if you're trying to compute things with more than 2 or 3 elements in a system, you're going to run into a computational nightmare. And that's been raging since the 1920s, right? There is no good way to solve these integrals. They're very complicated. Plus, there is no good way to directly look at what the wave function is, right? It doesn't give you any meaning, you have to apply an operator, right? You have to apply that question to the wave function in order to extract something meaningful out of it. And at the end of the day, like, what really is the wave function? It's the square root of a probability density. What does that mean, right? Chemists don't like that lack of intuition. And if you're dealing with that type of system, when it comes to molecules, you mostly care about geometry, energy, dipoles, maybe the spin of electrons, every now and then the shape of the molecular orbitals. And so around the 1960s, two guys decided that it might be worth looking into the electronic density, rho, and see how we can extract information out of this. So instead of minimizing the energy by using the wave function, what if we minimized the energy using this new description, this electronic density function? And that's how we start approaching the famous density functional theory. The issue, however, with the density function is that minimizing its energy involves two elements, right? The Coulombic attraction, as we shall see, between the nuclei and the electronic density, the electrons, and this F of rho, which is going to account for the electronic interaction between the electrons in the system. And that's going to be big F of rho, so it's a function of a function that's called a functional, and that's how you get the name functional density functional theory. Issue being the functional F, it goes back to the blind elephant analogy, in which an elephant comes to a village of blind people. Each of them can tap on the elephant and reach different parts, and they claim it to be different things, but no one can see the whole elephant. The functional is kind of the same thing. We know the limits and we know what these functions should look like on the extremes, but no one has a clear, explicit, analytical expression for a random functional, and that's just can't be done. And so it's this trade-off between having to deal with a non-intuitive, nightmarish type integrals from the wave function, which comes from pure quantum mechanics, or having to deal with this poorly described, but a bit more intuitive electronic density function. And that clearly motivates the question, well, before we had a way to find the best wave function, how do we find the best electronic density function? And as you would expect, there is this nice correlation between a wave function and its electronic density function. You can go from one to the, you can go from the wave function easily to the electronic density function, not so much the other way around. Fortunately, there is this nice theorem which states that both, that because of this property, the electronic density function follows the same limits as you would expect for the wave function. So it still follows the variational principle, which is pretty useful. As we saw, it's the way to gauge your system. And when it comes to actually computing the energy of a system using the electronic density function, you go through this little monster, right? The first element of which corresponds to the kinetic energy of your system. And for that, we talk about Jellium. It's a concept I'll dive into a little bit, just a bit. But it's a clear, perfect, solvable part of your equation, not so bad to work out. It's just a simple integral. The second element is also pretty okay. It's not any worse than we had with the original wave function, right? It's a standard Coulombic nuclei electron interaction. And at the end, we have the main enemy for this type of calculation, the electron-electron repulsion potential, which in this case here is described classically, right? It's essentially charge times charge divided by distance, which leads to some issues. You have to divide everything by a half to account for the double counting of electrons. And as a result, it's not great, right? You have to apply certain corrections. Anyone familiar with quantum mechanics might know fermions have some interesting properties. They tend to inherently repel even without accounting for charge. The expectation value of their separation over space is a bit larger than it should be. And so you have to start accounting for this exchange correlation, the exchange correlation energy, which is this little adjustment to your potential energy in your system. And this is how you start to get the different kinds of density functional theory, because there are different countless ways of accounting for this exchange correlation, for this extra quantum weirdness in the repulsion between electrons. And you have the famous ones, the Consham method, the PW91, and there are the hybrid methods, which I'll mention later on. And it gets pretty nightmarish, but some of them are more popular and more useful than others. Going back to the notion of jellium, jellium is the popular name, which I personally love, for a uniform electron gas, which is this way to imagine the motion of electrons in a homogeneous region of space, and also a great way to abuse monkey intuition, right? As humans, we have a hard time imagining pure equations and assigning meaning to them, but as soon as you can draw a diagram or a general, more multi-purpose description of your system, you might be able to extract more information from it than you probably could from just equations. Most people feel more comfortable with this than just letters and diagrams on a blackboard. And the nice thing is you can extract, therefore, the kinetic energy of a system based on the electron density function for that system by using pure statistical mechanics. That's why the result from the previous page turns out to be exact, and why it has such a weird looking expression. But if you actually work throughout the units, it actually adds to units of energy, which is rather nice. And the second digression, if you will allow me, is a little bit more of a curiosity thing I found out while learning about computational chemistry, and it talks about the Fermi hole, right? Because of the Pauli exclusion principle, you know that two electrons cannot have the same orbital and the same spin at the same time, right? That's just prohibited. We do not allow it. As a result, if you have two electrons with the same spin, and I place one at the origin, and then I place another electron with the same spin somewhere in space, ignore electronic repulsion for a while, just place it somewhere in space. And I ask you, where is it going to be? Well, even ignoring electronic repulsion, you're going to say, well, it's definitely not going to be in the same spot because they have the same spin. And that's perfectly right. But what if the electron has the other spin? Well, then it can kind of be anywhere. And as a result, you get something that looks like this for your distribution, again, ignoring electronic repulsion. If I have an electron with an alpha spin at the origin, the locations that another electron with an alpha spin can occupy are restricted by the Pauli exclusion principle. And so as a result, electrons with equal spin are going to repel less because they are essentially going to be farther away on average than an electron with an opposite spin. Again, because of this cancellation of their wave functions by the Pauli exclusion principle. And this is essentially the reason why we have to follow Hund's rule when filling out electronic diagrams back in high school. I remember learning about these at first and being like, okay, but why do they need to have the same spin? Like, why can I not group them together? And it's essentially because of this, because by making sure all the electrons have the same spin, you're going to abuse that cancellation of their wave functions by the Pauli exclusion principle, which is going to reduce the total electronic repulsion of the system and therefore lower its energy. And it's just a very neat concept. And that kind of wraps up the first main section of this presentation, in which I would like to review everything and perhaps highlight a few things. The first of which is a nice book, How to Solve It by George Polya, which does a great summary of like taking general concepts out of something and making them applicable. Doing that to what we covered so far is, first of all, to never trust your oracles blindly, right? You need to find a way to put them in check. If you're going to be using something mathematically, find a way to make sure the results you're getting are reasonable or at least improvable. And that's how that's what you do with the variational principle. The second main idea here is that even complex things can be treated, at least to an approximation, as being the sum of their parts. That's how we build more complex molecular orbitals, by adding up smaller things whose description we know. And third, perhaps an approximate answer to the right question tends to be better than the perfect answer to the wrong question, right? It's much better to numerically approach your final result over time and be sure you're describing the system as you want, than to approximate the whole molecule as just being a harmonic oscillator, right? Something that's highly theoretical and perhaps too ideal to be actually meaningful. Further on, you want to find a way to contain monsters when it comes to computations. That goes for minimizing the integrals and especially finding the needle in the haystack, right? A good way to do this is to go from local minima, which tend to be discrete, and to ignore them by finding a continuum, finding something, a parameter you can vary continuously in order to get the proper result you want. And that's what we did essentially with annealing. And of course, you want to fight with the weapons you have. If you're a chemist, you're probably more biased towards this than your regular physicist, but monkey intuition works, right? Every now and then someone has a good idea that you probably couldn't have had otherwise. And there seems to be, especially in solid state physics, a little bit of a prejudice against doing this. And it's perhaps reasonable because the systems in solid state chemistry get complex very quickly when it comes to like spin correlations and the such. But that doesn't mean that everything you can do by following your intuition is going to be fundamentally wrong. And of course, the little side note about the Fermi hole, sometimes brute forcing your way through a problem will not be optimal, right? I think that's pretty obvious, but it's very easy to forget. The best way to solve a problem is oftentimes to just ignore it for a little while and the answer might come to you eventually. With that said, I'd like to present now the second section of this presentation, which is a bit more applicable. Like how is this research actually done, right? How do you actually apply what we did to simulate molecules and more complex systems? Well, if you're at Princeton, we have at our disposal the research computing facilities, which are essentially these clusters of supercomputers. We have the more famous ones, Tiger, Della, and of course, Adroit, to which essentially I believe all undergraduates have access, no questions asked. And that's very useful. And once you have like the computational power that's better than your home computer, you can go ahead and select the chemical software of your choice. There are plenty out there which vary from price to availability to open sourceness. The most famous one is perhaps by far Gaussian 16. It's the most versatile and widely used, especially for organic type reactions. And Princeton is going to have the license for essentially everything you need. Bear in mind, however, that most of these softwares have been coded by chemists, and so they tend to be this weird amalgamation of Python, chemical knowledge, Fortran, C, and they all run in the standard Unix type software. So be patient. Like it's hard to understand the code and learn how to do it, but it's doable. And once you have all the basics out of the way, it's time to start modeling things, right? You want to find a good model for your system. Perhaps the most famous one within density functional theory is the B3-LIP functional, which is an abbreviation for Becky 3-parameter Lie-Yang par. Because again, the main enemy in density functional theory is finding a way to account for electronic exchange, and there are different ways to do it. In the B3-LIP method, they use primarily this selection of different elements with 3 parameters that have been optimized by Lie, Yang, and Parr over time. And it turns out to be a very good way to capture electronic correlation in a numerical approach. So much so that in this review, I believe from 2007, like a huge chunk of computational research is done using B3-LIP because it's a good compromise between accuracy and computational power. It's both relatively cheap and gives you reasonable results. And that's not to say, however, that there isn't any competition. There definitely is. But even today, B3-LIP remains as this overwhelming majority type research because it's so easy to deal with. However, as you would expect, there are plenty of options. You have all sorts of ways to describe electronic correlation. You can play around with things here and there. And these are all just some of the models I took from the Gaussian 16 webpage. But once you go and you select your cluster, you select your program, you select your level of theory, it's time to select the basics, right? The basic functions you're going to be using to build up your system from the ground up. When it comes to the linear combination of atomic orbitals, the thing you want to use is, of course, the Slater type orbital. It's this perfect solution, or at least the generic shape of it, to the hydrogen atom in the 1s orbital. The issue is, I don't believe this type of equation is solvable for double and triple integrals. And so it's just nightmarish. And so what most people do is they approximate this system with a Gaussian function, because you may recall from calculus 2 or 3 that Gaussians tend to integrate easily. It's easy to integrate them over space. And so they end up being easier to compute. And the best thing, they can be added together to approach the Slater type orbital, which, as you would expect, gets more difficult the more functions you add. You can start getting more nuance in your system by putting together more and more Gaussian functions and adding them one to the other to approach the Slater type orbital. And that's what starts giving the general nomenclature for the computational chemistry basis sets. A triple zeta type function involves adding together for the valence electrons 3 types of functions: the tight, the medium, and the loose functions, whose parameters are going to vary depending on the degree of resolution you want to add to your system. So if we think back to the building up of our atomic orbitals, we use the same procedure. We add together functions in order to get another function. In this case, the parameter to be optimized is the alpha in the system. And it's probably going to have been optimized by a graduate or an undergraduate student in their research before they released things. And bear in mind, however, that this doesn't work so well for heavier atoms, as we shall see later on. For that, you want to use different types of basis sets because of the number of electrons. And at the end of the day, it's all a compromise between how accurate you want to be and how much time you have, right? It's one thing for the simulation you're running to finish in 1 second, 10 minutes, 1 year, or 10 years, right? It's going to really be really dependent on how much time you have or how important the results of the simulations are to the research you're doing. So just as a proof of concept, it might be interesting to run through how these basis sets are read. In this case, the famous 6,311 plus GDP type basis set. 6 indicates the number of functions you're adding together to come up with the core atomic orbitals. That is the atomic orbitals that are going to describe the core electrons of your system. So if you have carbon, the 1s orbitals, they're going to have 6 functions, and that's it. Nothing more, nothing less. The 3 indicates the number of tight functions, that is the number of functions whose parameters are not going to vary much for the valence orbitals, in our case, the 2s and 2p electrons in carbon. The 1 indicates the medium functions, whose parameters may vary slightly, and 1 loose functions, parameters you're going to allow to vary a lot to account for polarizability. Say you have a fluorine atom bonded to your carbon, you want to make sure the electron density is being pulled away from the carbon into the fluorine atom. The plus indicates the addition of diffuse type functions on non-hydrogen atoms. This is especially useful when you're dealing with electrons in ions, right? If you have a charge that is essentially isolated and the electron is just looking at that positive charge. And the D and P in the lower sections indicate polarization functions, which are used to, again, keep on adding nuance to your system. Even though non-hydrogen atoms may not have D-type orbitals, like oxygen technically does not have D-type orbitals, we can pretend it does. And by doing so, we can account for changes in shape in the orbitals of oxygen more accurately than we probably could have without that polarization function. And you can do the same for hydrogen atoms. And this is just one of the more popular methods for breaking down basis sets. And there are lots and lots of options, right? And they're going to vary in accuracy and scope and what they can do and how limited they are and how fast they run. And it's always good to bear in mind that if you're selecting a high definition level of theory, you should also be selecting a high definition basis set. There's no point in not matching one to the other. Otherwise, you're just overspending computational resources. And so you finally have that. You have that basic knowledge. And now you finally want to simulate a general molecule. But you have no idea how to start because there are plenty of options out there. And I believe anyone has versatility and a proper knowledge of all the basis sets that can be used. So a good first guess is, as you would expect, to go to literature. Say you want to simulate a compound involving palladium. So you Google palladium DFT Gaussian. You select the first article out there, and you start following the citations and methods they use. As you would expect, here they use Gaussian 98, which is the previous version of Gaussian 16. They use the B3lib basis set. They select the more complete 63111 plus DP basis set. And for the palladium atom, they use the small core VDZ, that stands for valence double zeta type function. Because, as I mentioned before, when dealing with transition atoms, they tend to have too many electrons, a lot of which you don't care about. Palladium has a whole completely filled 3D type orbital. That's 10 electrons right there. And you don't really care much about those. They're not going to be involved in bonding all that much. And so you don't want to be spending computational resources on those not so relevant systems. And so what you can do is simplify the whole calculation by selecting a better basis set for your system. Thankfully, there's this nice website called Basis Set Exchange, which allows you to essentially look for the proper basis sets for each atom you want. And you can do this for more than just one atom. However, as we saw before, blindly trusting oracles is the worst way to do anything really in life. And so you want to have a way to probe the efficiency of your model. If you have access to experimental data, that's the way to do it. If you have X-ray analysis, you now have a solid way to find the geometry. And now you can compare the geometry from the computer to the geometry of the real thing and see how far off you are. Cyclic voltammetry might give you an idea of the difference in energy between the highest occupied molecular orbital and the lowest unoccupied molecular orbital. If you have UV-vis absorption and emission, you can use time-dependent density functional theory to look for transition bands and see how they should behave. TDDFT is a whole can of worms I won't dive into, but it's essentially a more nuanced expansion of density functional theory to account for transitions in time, which essentially involves transition between different electronic states. However, as you would expect, if you can measure something, you can calculate it on a computer. And so any type of experimental evidence you have can be used to probe your model. You can use NMR type calculations. We can do infrared, which is very useful for rotational and vibrational modes in your system. And even more abstract notions such as redox values, bond dissociation energy, excited state absorption. However, some approaches are better than others. Perhaps the most useful one when it comes to computation is to abuse error cancellation. And that usually involves choosing a good theory and basis and sticking to it throughout. And wherever possible, abusing subtractions, right? There are different ways to correlate electronic shielding and chemical shift in an NMR machine. And there are different ways to do it computationally. I found when doing research like 3 different approaches. The one that I would trust the most and the one that gave me the best results was the most simple one, was subtracting the actual compounds shielding from the reference. And that's a good way to abuse error cancellation, because if I'm overestimating or underestimating certain properties in my reference, I'm going to probably be doing the same to the compound I'm interested in studying, something that's perhaps not as well captured in different types of linear fits, which leads me to a third digression, right? The notion that subtractions are very friendly. They are a good way to cancel out and only look at the change in a quantity as opposed to the absolute value that quantity yields. And that is all present throughout chemistry and physics. We just do not pay as much attention to it as we probably should. Right? When it comes to ionization potential or electronic affinity, these are all subtraction type quantities. When you're computing energy in solvation, that's what you're doing. Like, how do you estimate the solvation energy of a system? Well, you pretend that you know the energy of the system without your solute in there. You put the solute in and you try to estimate how much of a disturbance that solute, that molecule, is going to have in the surrounding solvent molecules. And that's great for a computer, right? Computers can only do what we tell them to do, and sometimes we do not know enough. Another little more heartwarming system in this notion is to follow your intuitions a bit, follow your heart, and have some trust in the system you're doing, and try to extrapolate and predict variables, right? If you have access to a computer, you can start computing things that cannot be observed experimentally as easily. And perhaps the best example of this is bond dissociation energy, which can be obtained by the subtraction of energies between the system as it is and the system with broken parts, right? If you have an MR bond and you want to break that bond, you can compute the energy for that. And then you can run a potential energy scan. That is, you can compute the energy as you stretch that bond bit by bit on the computer, and you can compare them. And you might see some reasonable agreement. You see that the absolute change in energy caps off for most things at what would be the proper change in energy of the separate elements. And you can do the same for electronic absorption and emission. You can explicitly compute the change in energy as you change manually the spins of the electrons. And then you can compare that to time density functional theory, which does all of that automatically for you. And you can see how good of an agreement you get and how far you can go. And finally, perhaps most, I'm going to say visually appealing to most people, is playing around with population analysis of the molecular orbitals, which again is a way to abuse the monkey intuition once again by visualizing explicitly the shape of molecular orbitals. I was investigating this one bond in this one compound once, and I took a look at the energies of the molecular orbitals, and I saw that there was this trend of like a clear, there's something dropping in energy. And the question is, okay, what is it and what does it look like? And so you go into the shape of these orbitals and you try to make sense of them. At equilibrium geometry, you don't see much. But as you start stretching that bond within what would be reasonable for an IR type vibration, you start seeing that the orbital that's dropping in energy is the one that corresponds to the anti-bonding orbital between the bond I'm stretching. And that's the change in shape we get as we go from the left to the right image up until it gets to the point where the lowest unoccupied molecular orbital turns out to be precisely that orbital that accounts for the bonding. Which leads me to our fourth and perhaps last digression, but also one of the, perhaps the one that taught me the most over this past couple of months, is the active reimagination and resignificance of elements in science, and trying to describe things under a different lens. The big realization is that atoms and molecules are just one and the same, right? You can treat molecules as just weirdly shaped atoms. They are atoms whose nuclei have been split apart and separated in space. But aside from that, they are one and the same. The electron doesn't care. It doesn't see a difference between a pure nuclei and a bunch of nuclei spread over space. And with that, images such as this, which describe the molecular orbital, the shape or the regions where the electrons are supposed to be, they kind of gain a new significance, right? They're now, okay, this is how the electron minimizes its energy in this system. And once you start thinking of things like that, you might remember that light has this wave-like nature, right? It's essentially wave-ish. And in the UV-Vis region of the spectrum, it tends to be about down to 100 nanometers in wavelength. And a large molecule, one that stretches in a line with 100 atoms, well, that's about 1.5 angstroms per atom, so about 15 nanometers. So at the end of the day, a molecule is relatively small if compared to the wavelength of an incident light source. And as a result, we get this weird situation in which the only thing that matters for light excitation, that is for light passing through a molecule, is the change of the electromagnetic field over time. You might recall from physics lectures that light is an electromagnetic wave, a change in the electric field. And that is a change in the electric field over space. But as we see, space doesn't matter. The molecule is much, much smaller than the light that hits it. And so the only thing that matters is the change of the electric field over time. And that's essentially the frequency. And suddenly you have this more intuitive description to how electronic excitation happens. You shine light with the right frequency in your system, and you're essentially changing the electric field over the molecule, which interacts with the electrons, and it starts reshaping in the proper way the molecular orbitals of the molecule. And you can kind of abuse this a little bit and abuse the notation to claim that the light is shaping the molecular orbitals up until they have the shape of an excited state. And then boom, that's the excited state. There is no transition to be imagined here. It's just this squishing and squashing of the molecular orbitals up until the elements have the proper shape. And finally, extrapolating these elements to a more general sense, what we're essentially doing here in computational chemistry is taking a look at reality, what we know and expect to know from molecules and electrons, plugging it into a computer and expecting to get reality back. But as you would expect, the bigger, the weirder, right? The more elements you have in your system, the harder this issue gets. And so you have to find a way to filter away the over cost of computation. If you have up to 100 atoms, that's okay. More than 200 atoms, you have to use onion type approaches in which you apply layers, where you apply a high resolution system to your most interesting region in space, and then a lower resolution to surrounding regions. You have to account for solvation. That's a whole can of worms I won't dive into. But the best thing is that these principles are applicable to other fields of science, from atmospheric science to solid state physics to city traffic, right? You can model city traffic using AIs and these general simplifications, fluid dynamics, rain and fires in the rainforest in Brazil, right? There isn't really a limit to what you can do with this. And this leads me to essentially the conclusion, the main takeaways from this. The first of which is perhaps to always try to approach new things by amending previous ones, right? A good way of solving a problem is usually asking if you know a related problem or something that's similar or that has been solved in a similar way, which connects really well to the perhaps main pillar of science in sharing your results, right? If you're trying to solve a problem about a given photocatalyst, someone might have solved something similar at some point in time. And that might help you. That might be a good starting point to what you have. That said, always be a bit distrustful of computers that are bigger than a room, right? They only do what you tell them to do, and you might think they're doing what you meant when they are not. And so you always need to keep things in check. And the way to do it is to use experimental data. And of course, wherever possible, to abuse error cancellation to make sure the computer can counteract its own limitations by the way you set up the experiments. And of course, finally, try to reimagine things every now and then, right? The first idea you have will probably not be the best one, and there may be a better way to thinking about the problem you're trying to solve. It just might take a little while to get there, and you might stumble across what's a good solution for it. And with that, I'd like to thank everyone for your time, and I'll be happy to try and answer any questions.
Thanks, that was a great overview.